Okay, guys, thank you very much, and sorry about that. So I was just trying to put that in the Zoom form. That's why it's taking, it wasn't successful, but it's working now. Anyway, so what you were saying is this. Assume, for instance, that you have a rectilinear motion and a motion of speed, that a motion with a constant speed has an acceleration gamma or a, an acceleration vector gamma or a, that equals 0. Okay. So now what I want to prove here is if there is a curvature on the trajectory, then a motion with constant speed doesn't always have an acceleration vector that equals 0. So let's see how. So for that, let's find the acceleration vector and its magnitude for the motion of a particle which travel around a cycle. So the cycle represented like this. Travel around a cycle with radius r and constant speed v. Okay. So my objective is to find the acceleration vector for this case. Once the acceleration vector is found, we will see that such acceleration vector has a non-zero, well, actually a magnitude. Okay, so if we have the motion that is like this, I can parameterize this trajectory using the parameterization of what? Well, using the parameterization of a cycle, where each position on the trajectory is actually represented by an angle theta with the horizontal line L. And I better call it the angle theta. And here, I just have here the radius, that is the constant r. Okay. And this trajectory can be materialized by r of theta, which is r cosine of theta for the first term. The second term is r sine of theta. So r cosine theta, r sine theta, which I can factor into r cosine of theta, sine of theta. Okay. But if I have the trajectory that is happening at a constant speed, I can find what is called the angular velocity. So the angular velocity is the rate of change of the angle with respect to the time. That's it. I mean, if I move from this point to another one, there is the change within the angle theta. So if I take theta 2 minus theta 1 divided by theta 2 minus T2 minus T1, this will be some omega average. And this omega is just a delta theta divided by delta T, which is the omega. Okay, delta theta divided by delta T. If you're doing this instantaneously, then it's d theta with respect to T. And this will be called angular velocity, right? The rate of change of the angle with respect to T is the angular velocity. So the angular velocity notation is W, and it is theta divided by T. So in my factorization over here, on my decomposition, on my parametric equation representation of the trajectory, the circular trajectory that happened, for instance, at the roundabout, then I'll have the theta, which is omega t, the angular velocity being omega. Since the motion happened at a constant speed, then the omega will be a constant term. I will change my trajectory as a function of parameterization as a function this time of t, and that is r cosine of omega t with the sine of omega t. And from there, if I take the derivative, that's the velocity. It's the r is here, but I'll have minus omega sine of omega t, chain rule, and this will be omega cosine of omega t, another chain rule. Okay, so I can take the omega out. It's r omega minus sine of omega t cosine of omega t, and I'll find the speed. And to confirm that with a constant angular velocity, the speed is constant. The speed is the norm of, so that will be the norm of what? The velocity. So the norm of the velocity here will be r omega, the norm of this vector. So what is the norm of this vector, guys? What is the norm of the vector that I just put the norm symbol within with? What is the norm of such vector? Yeah, that'll be 1 because of trigonometric relation. So the speed is just r omega, which is constant. It's just to prove what I had my previous claim. If you have a constant angular velocity, then yes, your speed will be constant thanks to this demonstration, which is more a physics type of demonstration that I've just done. Okay. All right. We know that the speed is constant. Let's find the acceleration. The acceleration is the derivative, first derivative with respect to the speed, not the speed, the velocity vector. So if I take that, that will be our second derivative with respect to the position, doesn't matter. So if we take the derivative with respect to t of this term, another omega will pop up here. That will be minus omega cosine of omega t minus omega sine of omega t. So which is here. I can take the omega out. That become r omega square cosine of omega t, the sine of omega t. All right. And so the norm of this vector is just this with this norm, and this norm equal 1, and that will be r omega square for the acceleration vector magnitude. So we can see that this motion, the one that I just described, has a constant speed, but its acceleration is not 0. As a matter of fact, we'll be seeing later when we learn the decomposition of the acceleration vector, which is very soon, we'll be seeing that all the motion acceleration becomes centripets, the tangential component of the acceleration, the one that the decomposition with respect to the unit tangent will be 0. And I'll be specific on that when I discuss the decomposition of the acceleration vector. But my point over here is, if you take a motion on a trajectory that is not rectilinear, and you have a constant speed type of mechanic, then your acceleration is not necessarily equal 0. Any question, guys? Any question? Yeah, let me see the chart. There seem to be, no, it's the old, okay. Are there questions for me on all this that you've done, motion in 3D? Let me summarize that. We said that if a position vector of a motion is given by its component, so then the derivative of such position vector is the velocity. The second derivative is the acceleration. Okay, then we went through some examples. The last one is to prove that if the trajectory is not a rectilinear one, then there are some motion for which a constant speed type of motion does not imply that the acceleration is 0. That's it. Okay, those are the demonstrations that I did previously. Doing my homework assignment, this will become clear. One of the challenge of this summer class is the compression that is around it. So that's what maybe you're feeling, but I can tell you that other people who take this summer class previously, especially with me, has a lot of benefit doing that, especially working the assignment, and I know you can feel it. As for my friends who are playing game, and it's not the case of everyone that is here, I can see that you guys are very serious. The one who are, I don't know, maybe they're challenging themselves in doing multiple things, that's a bad strategy. And they cannot count on me to just pass the class without doing the work. As a matter of fact, I've seen 2 students that were not online yesterday but did the submission. I just want to remind them that the policy of the department is to come. Okay, I'm not talking about you, Miss Zank, but there were 2 students like that. They did the submission, but they were not on the roster of the exam taking. So I'm going to give them 0 because I have the name of the people or the student who took the test with these online things. Thank you very much, guys. So let's continue our discussion or our lecture. If you don't have any further question, I want to discuss with you another topic that is interesting about this motion in 3D. That will be how I decompose the acceleration vector in the TNB triad, in the TNB frame. So if the motion has a trajectory like this, okay, it's a 3D trajectory that I'm interested in for this case, all right? So at each of the points here, we said that there is a tangential and normal component, okay? Well, tangential components, well, we have a tangent line to the graph at this point with a unit tangent like this, and the normal that is orthogonal to it. Now, if I have an acceleration vector which is associated to the motion at each of the points, I can, if the acceleration vector, the acceleration vector will remain within the what we call the osculating plane, so the plane formed by T and N. I want to see, since it's not, it can be oriented only in the T direction and only in the N direction. We just have seen one of them, where on the trajectory like this, the acceleration is a centripede like that. Well, it means the tangential one does not exist. Now, if it is, any arbitrary motion, and I have the acceleration vector like this, at each of the points of the motion, I can decompose this acceleration into a tangential and normal component, by using the rule of projection, if you want to see it like that. And the objective that I have, or the objective of this section, is to be able to tell what is the tangential component. I mean, what is the magnitude of the vector if you do the projection here, and what is the orthogonal. This is the parallel projection, and this one is the orthogonal projection. So we want to see what is the parallel projection component, what is the orthogonal projection component of the acceleration as a function of what? Well, as a function actually of, I would just say, the parameter of the motion. Mainly, those parameters will be, or the parameter, or the geometry, yes, the geometry of the trajectory. There will be the arc length, there will be the speed, there will be the curvature. So we want to decompose such acceleration vector as a function of its tangential and normal component. Let's see how. So I'll depart from some algebra. It will be a mix of algebra and geometry. Okay. So at the very beginning, we know that the velocity vector is the derivative with respect to t. If you prefer s, that's fine. But since what you have over here is mainly a mechanical motion, then our derivative will be as a function of the time t, r of t. Okay, so let's see that. If I have that, then I can find the acceleration as the derivative with respect to t of v. So since, take a look at here, I have v, the derivative with respect to s of, with respect to t of r of t. Then I can use some algebra. The algebra involve the arc length here, and introduce it because of the chain rule, ds over here. So that will be d with respect to ds of r, which regular multiplication is not a dot product here. So of ds with respect to t. Who knows why this is not a dot product? This is not a regular dot product. Why? Why is that? Why is it that it's not a regular dot product? Okay, so another way to express the question is this term, what is this term? D with respect to t of s, what is it? Let me see if there is something in the chat. No, if I want to find s is the arc length, okay? So if I take the derivative with respect to t of the arc length, of its arc length function, what do I have? Yes, it's a scalar, thank you very much. So since it is a scalar, if this dot here was just a regular, it shouldn't be like that. I should put the d with respect to t of s, scalar multiplied by this term is a vector. Okay, so this d with respect to s of R, well, it's in the direction of the unit tangent t. So from there, I can find the acceleration A of t. Sorry, the acceleration A of t then is the derivative with respect to t of v, which is the derivative with respect to t of t d with respect to t of s. Okay, same term that I have here. Then from there, so the d with respect to ts is somewhere over here. Okay, so from there I can use the product rule. Okay, product rule for the multiplication. Then that will be the derivative with respect to t of ds with respect to t. Derivative with respect to t of d with respect to ts. So that's the second derivative with respect to t. So it's like this. Scalar multiplied by t plus then, well, this term, derivative with respect to a t of s, which scalar multiply derivative with respect to t, the parameter t of the unit tangent t. All right. Then now, I start to have interesting information because my objective is to find the decomposition of the acceleration vector as a function of its tangential and normal component. Then I already have the decomposition in the tangential component sense, because here I have the unit tangent t that is here, and then it's the component with respect to t would then be second derivative with respect to t of s. And we'll see later that's what this corresponds to. And then from there, but we can just do some algebra a little bit over here. If d with respect to dt, well, what is d with respect to t, by the way? Nobody respond to that question. S is the arc length function of the arc length. If I take the derivative with respect to t of the arc length function, I find what? I find what, guys? Okay, so let me rephrase it like this. The integral from a to t, the norm of r prime of u du. So if you take the derivative with respect to t of s, what do you get? What will be the what will be the answer? Yeah, that's exactly, that's the speed, v of t. So we see that this is the derivative, this term will be the derivative with respect to t of the speed. Okay, so that's the tangential component of the acceleration. Now, what I need now to add it to this is the normal component. I already found the tangential component as the derivative with respect to t of the speed. Okay, I need now the second component, which is the normal component of the acceleration. We will see that it will depend on the curvature of the trajectory at such point. Let's see how. Okay, the how is this. I'm going to keep doing these algebraic things of adding and subtracting, multiplying and dividing. So I will, in this term, I will divide and multiply by ds. So the ds is here and ds is here. I didn't do anything. But I know that this term, d with respect to t of s, it depends on n. Why? Because the unit normal component is the derivative with respect to s of the unit tangent divided by its norm. That one, we've seen it. Okay, these are not complicated if you keep reviewing your stuff. So then this vector then, well, is just what? This term, the norm of d with respect to s of t. What is it? What is the norm of d with respect to s of t? Absolutely, that's kappa. Okay, that's the curvature. That's the first definition that I have for the curvature. So that's curvature at s. And that's, I then replace this expression with the expression which is here as kappa, which scalar multiply the unit normal vector, which is changed here. So I have a constant term here, another constant term over here with the n that goes out, and I'll have d with respect to t of s multiplied by another d with respect to t of s, which multiply the curvature scalar multiplied by the normal component of actually the unit normal n. Okay, so let me finish that. So I have this, which is the tangential component, and the normal component will be the curvature, which multiply the derivative with respect to t of s raised to the square with n. Okay, so this will be the tangential component and the normal component. So with a zero term at the end over here. So what I'm looking for, the tangential and the normal component, the first tangential doesn't involve, the tangential component does not involve the curvature. So that will be the derivative with respect to the time of the speed. And then the normal component will be the curvature, which multiplies the speed to the square. So you see that in our previous problem, since the speed is constant, the tangential component, which is the derivative with respect to the speed, is zero. That's why all the motion then is in the normal component. It's just, a quick example, so we move this forward. So if I have an acceleration vector and I want to decompose it into the normal and tangential component, I know that the tangential component does not involve the curvature of the motion. And that will be the derivative with respect to the time of the velocity, the norm of the velocity, which is not always constant. Keep that in mind. And the normal component itself is the curvature, which multiply the magnitude of the norm raised to the square. Any question? I'll do some example with this, but do you guys have a question for me? No question? No question? Okay. So then with this, since we know, or we just derive the tangential and normal component as a function of the speed and the curvature. Okay. So I'm interested in an additional theorem which I call acceleration vector theorem. So if you give a motion, given a motion in the 3D, you can decompose the acceleration vector into the tangential and normal components like this. Okay, and we also will have the following formula. Besides these two formulas, the tangential component is A dot T. I will prove that. It's also, you can change it into A dot V divided by the norm of V, like this. And the normal component is A dot N. You can also change it into the root of the magnitude of the acceleration vector to the square minus the tangential component raised to the square. Okay, so all I'm saying is if you take the AT or the A sub T, A suffix T, so the tangential component is the derivative with respect to T or V, but it can also be expressed as A dot T or A dot V divided by the normal V, okay? Or the normal component, which depend on the curvature, can just be expressed as A dot N, but because of this right angle over here, then this square is the tangential component or the normal component raised to the square plus the tangential component raised to the square. So at the end, this is easy to see. That will be the root of the acceleration vector, the norm of the acceleration vector square minus AT raised to the square. We can also express the AT, this whole term as A dot V divided by V dot V in the V direction, which represents the projection of the vector A onto the vector V. That's how we define the projection, right? Projection of A onto V. So it's A dot V divided by the normal square of V in the V direction. And since this relation is true, the AN T, the normal component, scalar multiplied by the tangential one. Okay, so that will just be A minus AT with T, which is A minus the term that is here. That said, I can prove this formula quickly. This one we already see how. So this one is easy. So who knows why? AT is A dot T. How should I do that? If I want to check that A dot T is AT, well, it's easy, right? I just need to write the acceleration vector A. We said that the acceleration vector is ETT plus A N N, like this. So if you dot with T, since the N and T are orthogonal, so this term will be what? The dot product of N and T is what? What is the dot product between N and T? 0. So this term goes away. So I'll have a T, T dot T. But T dot T, what is T dot T? It's the norm of T squared, which is 1. So that will give me 80. And the second demonstration is the same because over there, you have a t like this plus a n like that, but dot the vector n. Okay, so that will be t dot n. The t dot n is 0 orthogonality, and you have only a n with dot n like this. So this is 1, and that will be a n like that. So it proved that. And from this formula and the Pythagorean theorem, this also goes exactly like the one that, like the picture that we show over here. So there is no problem with these two formulas. So this one we can also prove it. It's not difficult. So all we are having over here is AT in the t direction, and the claim is it is a dot v divided v dot v in the v direction. But we need to prove that this term is exactly equal to this. Why? Why is it that I have a dot t, the acceleration vector dot t, which equals this? That seems to be obvious to me, but why? Why is it that I have a dot t, which exactly equals this? So my question is, if I take a dot t, why is it that I can write that it is a dot v divided by v dot v? Why? Yes, t is v divided by the number of v, so you just need to replace that, and you have it like this. So the claim over here is at, the tangential component scalar multiplied by t, will give you a dot v divided by v dot v in the v direction. Well, that's not difficult to see. The at is already found. It's a dot t. So since we are adding another t, so I'll have a dot t like this. So in the t direction, and this will give you a dot v like that with the norm of v like this with v and the norm of v. Okay, so the norm of v multiplied by the norm of v is the norm of v squared, and that the norm of v squared is v dot v in the v direction, and that's it. So it established this formula. So this one, well, it goes without saying, because you have this formula that is true. Since this is true, then this component is just the acceleration vector minus ATT, which gives us, because ATT, it's this term, so that will be A minus A dot V divided by V dot V, which scalar multiply the vector V. Okay, so I know it's a little bit brutal, but if you take your time and read the proof, or this proof, the one that I just did, it's a part of the textbook. I didn't go further than what the textbook is saying in this context. So you can use the textbook over there to understand what is the proof of this theorem. But the key point are, if you have a motion in 3D, so the triad, the TNB frame, okay, well, you can use it to decompose the acceleration vector into only the t and n. And the tangential component is the derivative with respect to t of the magnitude of v. And the normal component this, you can express this as a function of s. That will be the derivative with respect to t, the second derivative with respect to s. And this is the curvature with the derivative with respect to s raised to the square, like this. And that's it. Okay. So all of those formulas look, they are very simple. They are, there is nothing complicated about them. Let's apply them. This is the proof I described previously. Okay, so because the norm and this equals 0, then a dot t gives us a t, a dot n gives us a n. And this also is just the translation of the definition of t. We prove that. And the other one comes from, the Pythagorean theorem, because of the orthogonality between the tangential and the normal components. And then the rest follow. Let me give you one example to see how we can, how we can elaborate or explore this for further purpose. Look, in this assignment, your task to find t and n, okay? No, not find t and n, but we want to find the acceleration of this motion, and we want to write it tangential and normal component, okay? But we have to do the assignment without finding the t and n. Because if you find the t and n, then you can use it to find the unit tangent, I mean the AT and then the n. But if you don't want to do that, so the AN and the AT, we want to find it without finding t and n. Fine. Okay, write this acceleration form. Okay, so let's see how. We know that AT is the derivative with respect to t of the speed. So we need the speed. And then the AN, we need the curvature, derivative. Well, the formula is the formula, we'll see that later. So the curvature multiplied by the derivative with respect to t of s, so the speed raised to the square. Okay. Since the motion is given by cosine of t, t sine of t, sine of t minus t cosine of t, for positive t, you can graph this motion to see how it looks like. We can find first the velocity vector. The velocity vector allows us to find the speed, and then we can find the tangential component. Then we need to find the curvature. It's the curvature that allows us to multiply by the speed to the square to find the normal component. That's it. So we have 1, 2, 3 tasks to complete. First, this derivative, okay? For that, we need the v, the vector, the velocity vector, its norm, and take the derivative. So take the derivative each time. This will be minus sine of t plus sine of t plus t cosine of t. That's what I have here. Okay, so these two terms goes away. Thanks. So that simplifies my life. And this derivative is cosine of t minus another cosine of t, product rule here, minus, but actually plus t sine of t. So this goes away. So the velocity vector simplify into t cosine of t, t sine of t. Okay, so the norm that I can take the t out, if I take the t out, is cosine t, sine t. So if I take the norm, I will only have this as a t. So this term, the velocity vector, the speed, will just be t. Okay, that will be t. Why? Because if you take t, I have it here. T cosine of t, t sine of t. You can take the t out. Okay, or you can just do the square of this and this. T square, or this become 1. So the root of t square is t. And when you take the derivative to find the tangential component of the acceleration, the derivative with respect to t of t gives you 1. So the tangential component is 1. We can do many things to find the normal component. Maybe finding the kappa, if that's possible. But observe that the normal component is the norm of the acceleration minus at. We already found the at. But from this, we can also find well, the acceleration, because the acceleration is the derivative with respect to t of v. And then take the norm of the vector we found. And that can also be a fast track to go toward the solution of this problem. So if you take the derivative of this component, the vector, so that will be cosine of t minus t sine of t, which is here. And then this will be sine of t, okay, plus t cosine of t, which is there. Then there will be a little bit of algebra that will simplify. Thank you. Thanks to this, the shape of this component. That will take the square of this component, the square of that component. It's cosine square t plus t square sine square t minus the double product here, okay? Plus sine plus t cosine t, which is well, the cosine square t square sine square minus 2t cosine t sine of t plus the square of sine plus t square, and positive twice the double product in this quadratic. Yeah, that's the quadrant. Yes, that's a plus b squared. The standard form is a squared plus 2ab plus b squared. All right. Then with that, you see that these two terms cancel. And I only have this, which is 1. And I can take out the t square, factor the t square, sine square here plus cosine square. Then my overall result will be 1 plus t square. Okay. So since that's my a square, since the an is the root of the a square, 1 plus t square, I'll subtract minus 1. So that will be the root of t square, which is t. So my acceleration can be decomposed into a tangential component and a normal component. The tangential component being 1, the normal component being t, with t that's greater than 0. And in the frame, the t and b frame, I can write the acceleration vector as 1t with a 0 term for the z component, and that will be it. Okay. Well, there are many multiple examples that we can discuss, but I leave the rest for my homework assignments, and I have over the multiple and various type of assignments to see the multiple angle that this kind of topic contain. That's how you should be seeing it. So for those who are complaining on those Discord, etc., that's really the problem. They should not be taking this class. Okay, don't follow them. My advice is keep coming into class, do your best, and then take the maximum that you can take to continue. I teach this class several times, I don't know, more than 10 times. And I know how hard that could be depending on the circumstances. Some of the students don't come to learn, they just come for the grades. Well, this time that will not go like that. I'll make sure that they repeat the class during the fall. All right, guys, do you have question for me? Yeah. So at yes. I mean the unit. I mean the tangential and normal component. They are the parallel and orthogonal projection of the vector a, acceleration vector a, onto v. So you see that if I have a motion like this, v follow this trajectory, right? Because the tangent here, unit tangent is directing this, the tangent. So it's, the v. If the acceleration vector is like this, then the tangential component is like, with an angle theta over here, it's like I was projecting the acceleration vector onto the vector, the line that support v. So the direction of the vector v, and then the orthogonal projection will represent, in this case, the normal component of the acceleration. Did I answer your question, Iris or Iris? Did I answer your question? Yes, all right, great. Okay, I've said everything that needed to be said about chapter 14 that is necessary for this class. So we can start discussing a function of several variables, but I'm not going to overwhelm you. I just want to see if you guys have some question for me under the topic that we cover, or if there are general questions, then next week we'll pick it up from function of several variables. For function of several variables, we will mainly discuss what is the domain, what is the range, how do we find limit of a function of several variables, derivative of function of several variables, differentiability, partial derivatives, chain rule with partial derivatives, and some optimization problem. And that's all this is about. Plus the fact that you need to stay focused. Yes. Lowercase v in the acceleration theorem. No, for the v notation. No, the lower and uppercase doesn't, if you want to distinguish between the speed and the velocity, just do it like this, v. It doesn't matter whether you use lower or uppercase, as long as you have the arrow, it's said that it's the velocity vector. But if you write it like this, then there is a tendency of saying that it is the speed. But the reason why I use this is because in Rogowski, that's what you feel. It is hard to bold these letters, okay, in my note. That's the only reason why. But if you have a vector, just put an arrow over there, and that's it. Is it clear, my friend? In the proof of the theorem, for where? Which proof? Which one? Which one? Do you mean, okay, so let's see. It's good. You mean here, right? Yeah. No, so here is this vector is the unit tangent. The unit tangent is r prime divided by the norm of r prime. But r prime is v. and its norm is, I mean, the norm of V here. So you can put the bar here, the arrow, sorry, not the bar. You can put the arrow, you can put the arrow on the vectors. Okay, my friend. All right, great. So listen, I don't want to overwhelm you too much with this. I don't want to give the impression that we are moving at the speed of the light, but it's the compression of the class that is like that. So let's pause over here for this week. Next week, when we meet, we'll start discussing functions until the end of the quarter. Listen to me carefully for some of the recommendations that I have. I have 78 students who are on my roster, okay? Then I noticed that like 30 of them are coming into class. Today it dropped to 25 or something like that. I'm saying to those students that they are not serious. Some of them still cannot access the class. And then they say, no, it's bon. Listen, that's just hilarious from my perspective because my point is, since this is the third week, if a student doesn't know where to find the Zoom link or cannot enter, that means the student is not taking the class. Now, I don't want them to feel like because you're doing this exam online, they can be doing anything irregular. Because if I find out and I hear rumor, I'll cancel the whole exam for everybody. Okay, and then I'll inform the department on why I did that. So be careful. I'm not talking about my friends who are coming over here. We have to do this in a way that is serious. Please keep learning. And I know many of you are doing it. There are some of the students are just submitting their homework from time, even though I know that the homework can be lengthy, but it's for their training. But the students are doing it in this class. So we cannot go by the one who doesn't want to work. Okay, so we have to follow the students who are working. And, I wanted to thank them and to keep doing what they are doing so far. Thank you very much, guys. I wish you a great weekend and keep up with the hard work. And I'm going to, with my colleague, the TA, start, okay, so to do the grading and hopefully we'll get it done by Saturday or Sunday. Thank you very much for coming and I look forward to see you. And I hope you're having a great evening, night, wherever you're located in this point of the globe. And I look forward to see you next week. Bye-bye.